Let's start with Mr. Einstein. It was funny that I noticed he referred to all his colleagues, if the translation is correct, as Mr., not Doctor, as we do today. But in his case, it would be Mr., because when he wrote these revolutionary papers, he did not have a PhD. He got one afterwards. So now I have to always correct people when they refer to me as Dr. Lerner, since I'm Mr. Lerner. So who wants to start with, I know that this Einstein paper was pretty mathematical, and that certainly was his style. So who wants to take a stab at saying what was the core of Einstein's argument in this paper, and how did he defend it?
I'll start off with he came up with a number of occasions on which it looked as though photons were electromagnetic radiation was acting like a particle.
All right.
A number of different things. So one of them was, for example, blackbody radiation. Description of.
What was his first point? Because this unfortunately is, he starts out with his most complicated point. And we learn from the other author, R.H. Stewart, that even his contemporaries thought it was a little hard to follow. But what was his first point of evidence about quanta?
That wave theory did not fully explain the generation and transformation of light. Some effects of generation and transformation of light could not be, there was a contradiction with, could not be explained by 100% wave theory.
He's talking about the black body radiation in the first section.
Yeah.
Now, we know from our previous class that Planck was the first to postulate the correct formula for black body radiation, for the spectrum of the radiation. And he was the first to say that, well, what did Planck say about the reason for his formula? What did he say about the quantization of energy? People remember?
No, I don't remember.
I mean, basically, he was just introduced the idea that energy traveled like in quanta, like in little packets, and the atoms could only emit and absorb that energy in like these discrete packages.
Right. He said the second, not the first. He did not say that the energy was traveling in quanta. That's why Einstein's paper was different from what Planck had said. What Planck said was, my equation can be derived. So remember, Planck first came up with the formula. And then he said, how can I derive this formula? And what he said was, if the atoms that the black body consists of, so the walls of the black body, which remember is a cavity, which is assumed to be 100% opaque. That's why we call it black. That the atoms in the walls of this cavity are emitting and absorbing the energy of the electromagnetic waves in distinct quanta. So the energy is emitted and absorbed But that does not mean, it does not follow logically that the energy travels from one point to another. He and Planck absolutely did not think that at the time. Basically, he said, we know what the energy is like. It's these continuous waves described by Maxwell 40 years ago. We've been using it to develop this enormous technology by then. But the atoms can only take and give to this wave indistinct. So it's basically like you have an ocean, but you can only add to or subtract from that ocean in drops. You've basically got the eyedropper theory of atoms. I just came up with that.
But I guess in Planck's, it was like the water is getting added in like a stream. And then Einstein was like, actually, no, it's always traveling in droplets.
Right. And that was a revolutionary concept because Einstein knew, as well as everybody else, that the wave theory of electromagnetism had been well established. And, you know, people were already using that to build the transatlantic cables. Now, in 2005, was radio in existence? I forget. But obviously, the wave nature of electromagnetism was well established. So that's why Einstein was taking a big leap to say, look, yes, whatever we know about electromagnetism, okay, but here is evidence that there are quanta, that there are what we now call photons traveling from one point to another. And his first argument is basically mathematical. He's basically saying, up until the section on the generation of cathode rays, our videos come out of LPPFusion's research in fusion energy, the energy which will power a future of abundance for all, with a sustainable economy in a clean environment. Goods, housing, and transportation will be affordable to all once fusion kicks in. Fusion energy is the key to building a better world now. Support fusion research, $10 a month at lppfusion.com/support. The link is in the description. Thanks. If we look at the short wavelength part of a black body radiation. So remember what the curve looks like. The curve rises, goes to a peak, and then there's a slow decline towards longer and longer wavelengths. So the long wavelength part, longer than the peak, much longer than the peak, could be described and understood, and it was understood by classical electromagnetism. But the problem is, if you extrapolated that part of the curve to short wavelengths, it went to infinity. That was the ultraviolet catastrophe. The short wavelength part, where it suddenly falls over and goes into an exponential decline towards shorter and shorter wavelengths, that was the Wien part of the curve. And he says that can be understood by statistical mechanics if we simply substitute these hypothetical light quanta for the well-known atoms that Boltzmann's statistical mechanics were based on. So it's a mathematical argument. If you make this wild hypothesis you get the same result as the wine can. Then he gets into really the more interesting part, which is you make predictions from this wild hypothesis. And what's the big prediction that he's making and then verifying by the illumination of by the what we call the photoelectric effect? How is the photoelectric effect evidence for this hypothesis?
If I recall correctly, this is Elliot. The distinction was that the energy of the emitted electrons was proportional to the number of was proportional to the frequency of the photon coming in. And you simply had more electrons if you had more photons of the same frequency.
Right, exactly. Now, I find it kind of funny that if you look at, I don't have any page numbers on this printout. I don't know whether you, so if you look at the section on the generation of cathode rays, and you go down to see now whether the derived relation agrees with experiment. And the next phrase is, to me, a little funny, to within an order of magnitude. So I'll have to admit, I haven't looked up the details of why there isn't an exact agreement between his predictions and Leonard's experiments, where the gap, whether he left out a factor in his calculations or what. But certainly today, there's only one field in which we would consider agreement to a factor of 10 to be good agreement, and that's the field I deal with in my other hat, which is the field of cosmology. But in physics, if I said my fusion predictions are 10 joules and we got 1 joule, people would say, well, your predictions have to be modified. But here, when they're dealing with these new phenomena, where they're expecting something entirely different, qualitatively different, they're expecting the energy to be proportional to the intensity of the light. Because remember, we're dealing with a wave. The amplitude of the light is proportional to the total intensity. So it's not proportional to the frequency. So you're getting a result which is, it's basically at right angles to the result expected. Intensity doesn't matter for the energy of the electrons emitted, but the frequency does. So here, with his must have been considered by everybody a revolutionary or perhaps crazy hypothesis, he can make that link very easily. So that's why, to a certain extent, although it certainly looks somewhat amusing to us, he can say, well, this is roughly right. It's in the right direction. And then there is this correlation. Any other comments on this section or questions? So just briefly, what's his final point about ionization?
Whoops. Yeah, hi.
Okay. Does anyone want to, or do you want to comment on the final point that he makes under ionization?
It's all about the energy limit.
Right.
That the ionization energy per unit of weight equivalent cannot be larger than the light quantum energy.
So again, why is this proof or evidence of a correct prediction?
Because it correlated with the luminescence or or is it the cathode ray effect?
Now, it's the separate section, his last section. These are actually very simple equations, especially
Yeah.
compared with what he did later with general relativity.
Yeah.
If we look at the
other thing that I understood is that that each quantum of light energy ionizes only one gas molecule. It's 1 to 1.
right, he's making that hypothesis. And then he's basically saying that according to
16.
Leonard's measurements for air, the largest wavelength, so the smallest frequency that has an effect is 1.9 times 10 to the minus fifth centimeters, or we would normally call that 0.19 microns or 190 nanometers. So he translates that into his formula. Now, his formula uses, it's a little confusing because this formula uses the symbol R, and today we would use the symbol H. But what he says is a photon is going to have this much energy. And therefore, he compares the energy for the wavelength to the ionization voltage. So the ionization voltage is measured in an independent way by subjecting the air to a high potential. And then you see at what point, when the air starts to break down, how much potential do you minimally need? So that's ionizing the atoms by stripping them away with a strong electric field. And you compare that to the independent measurements comparing the wavelength of light that ionizes. So we see that, for example, in our experiments. In our experiments at the lab, we have the problem of pre-ionization. If the gas is totally neutral, when the big current hits, you're basically creating isolated sparks. And those sparks can be randomly distributed, and that doesn't give a smooth breakdown. So if you don't have symmetry, when you compress everything, you get poor compression. So we and others use a pre-ionization. And there are many ways of doing this. So one is a pre-ionization field, where before the big current, you put a field across the electrodes, and a small current starts to flow because a small number of the atoms are being stripped by the electric field. Number two, you can use ultraviolet light. You can pulse light that is more than this threshold. Each photon is more than this threshold to tear away the electron from its atom. And you can use ionizing radiation from a radioactive source. So you have some high energy particle bumping in and to the neutral atoms and ionizing them. So what he's saying is, if you compare two ways of ionization by light and ionization by an electric field, then they show the same ionization level if each photon has the energy that's defined by the quantum equation. So each has the energy we would term Planck's constant times the frequency. So that was what Einstein did in 2005. So any questions on that discussion? So the other piece is longer. Has everybody read the other piece? Stewart,
Yeah.
hands up, who has read the longer piece on the quantum effect? Lift your little orange hand. Where's that? Oh, the reaction symbol.
I haven't made it through the whole thing yet.
Okay. Peter, Martin, Elliot, Philip. All right. Sam partway. And who else? Okay. So those who haven't read it should read it. Oh, but the main thing is some people have read it, so we can discuss it. So does anyone want to summarize it? What's the main point that Stewart at Minnesota is making? Peter? Unmute yourself. Wait a minute, I was calling Peter Catalano.
Oh, sorry, because I'm down as Debbie, but I am Peter, really.
I know, you're both Peter, so I should say Peter C. What's your
Apologies.
Peter, what's your last name?
Which Peter are you talking to? Oh, me, Peter Saberin. I can't change the Debbie. I've tried to change the Debbie and I can't change it.
I know.
Well, all right, so it's the interaction of radiation and matter. I mean,
Go ahead, Peter. Peter C and Peter S.
right. I mean, it just says it in the abstract that it's the interaction of radiation and matter. The Compton effect was the decisive event in the transition to quantum mechanics.
Right, but
So the scattering in the Compton effect could only be explained by a billiard ball model.
But what is he saying about the difference between the real story and the story that the history books tell us?
Oh, that the Compton was trying to verify or falsify Einstein's work, which wasn't the case. He was doing his own thing.
Right, which is very interesting because, again, there's this tendency for the simplification of history, for reducing things to a straight line. Now, when I was learning this, it never occurred to me, frankly, that that's a really long time to try and confirm a theory, because, it really wasn't until I was reading this stuff over when I thought about it. Gee, 1905, 1923, that's 18 years. It's a really long time. Now, it's one thing, we did have, nearly that gap, something like that gap in the hypothesis and discovery of the neutrino. But the neutrino was a really tough experiment to do because neutrinos have very little interaction with other particles. But here we're dealing with photons, admittedly with X-rays and gamma rays. But by 1905, especially in the subsequent 10 years, we have a big development of this field. You know, this is already 10 years after the discovery of radioactivity, and you have a lot of research in this field. So, you know, what does this story basically tell about, as you say, Compton was trying to do his own thing. What was he really trying to do? And why wasn't he trying to confirm Einstein's theory or invalidate it?
Was he trying to explain why X-rays were, if the word is diffracted, I'm not sure, but his experiment was with the X-rays and why they were not in a path that was why they were not in a path that was not diffracted. I'm not sure the word is diffracted, but
I think it also has to do with the relationship between the wavelength of the X-rays scattered and the wavelength of the incident rays.
Right.
Yeah.
So, yeah, so that was a big difference between what Einstein was predicting and what the wave theory of electromagnetism, which again, remember, it was a completely validated theory. It was used in technology. People knew it was true. And yet, there was a big difference between what was predicted if the energy was being carried by photons rather than waves. And at this period, you know, this is before wave particle duality. People were saying, well, which is it? It's one or the other. So that was the problem. If X-rays were acting as a wave, then their interaction with matter would not change their frequency or their wavelength. So what the historian here is showing is that this was really very ingrained, and very few people accepted Einstein's paper. He was not honored initially for the paper on the photons. So, and he points out, like on page 977, that Millikan, who did experiments on the photoelectric effect, that in retrospect completely validated Einstein's prediction. In 1915, completely rejected Einstein's theory, right? Despite the apparently complete success of the Einstein equation, the physical theory of which it was designed is found so untenable that Einstein himself, I believe, no longer holds to it. Well, that wasn't true. Einstein never repudiated it. And we were in a position of having built a very perfect structure and then knocked it out entirely without having the building to fall. So he accepts the experiment. Well, he did the experiment. Experiment confirms the theory, but he still doesn't accept the validation of the theory, which is against the scientific method. And then he points out that writing many years later, in 1950, he completely revises his own history so that he was saying, oh, I confirmed this prediction. Well, he did confirm the prediction, but he didn't think he was confirming the theory. He only thought so, in retrospect. So what's interesting to me is that Compton started out with an entirely different interest, which was to investigate the magnetic properties of the atom. So he basically said, if the atom is magnetized, then electromagnetic theory says with a sufficiently strong magnetic field, you should be able to change the direction of the polarization of light. And he was frustrated, right, because he didn't get that. So what was his next step? All right, well, I'll give everybody 2 minutes to try and find from the reading what the next step was. I have to excuse myself. I'll be right back. Okay, what's the answer?
Gamma rays and the fluorescent Doppler effect.
Well, but there was an intermediate step.
The ring electron,
Right.
the ring-shaped
You want
electron.
to talk about that? You want to describe what the ring electron was?
The X-rays were diffracted by a large ring-shaped electron that would reduce the scattering. I don't fully understand what he's saying here, but he says reduce the scattering coefficient below the Thomson value. I know what I'm saying, but I don't fully understand it.
Right. Anybody else want to follow up on this? This is on page 980.
Yeah, so he was decided that as you say, the size of the electron, well, the electron was doing the scattering was the first thing, and then to calculate how that could be the case, he had to have electrons to be of the same order of magnitude of size as the wavelength of the incoming radiation, and that meant that electrons had to be rather large.
But I don't understand if he means that there are more than one size of electrons, or that all the electrons have a different shape. So I really did not, or that the electron is normal, but it has some kind of field effect that enlarges the effect of the electron to this large ring. I don't really understand what he's saying there.
What he's saying is he's trying to put together two numbers, at least two numbers, which is how much the radiation is scattered and the wavelength that it's scattered, that is the dimension of the object that's doing the scattering.
Mm-hmm.
So if we have everything what we now call classical, then what you have is waves bumping into solid objects, right?
Mm-hmm.
So if you have waves bumping into solid objects,
Mm-hmm. Yeah.
to
The
have
larger the curvature of the object, the longer the wavelength of the reflection,
the diffraction.
the refraction. Yeah.
In other words, let's just think about water waves. We can get rid of the
Mm,
other dimension. It doesn't really matter.
mm,
So let's say we have piers and a wave is coming against the, the supporting beams of the piers, which have a certain diameter and are regularly spaced, like the atoms in a crystal.
mhm,
If the waves are much longer than in wavelength, then the spacing between the piers, then there will be no diffraction. In other words, a certain part of the wave will be blocked, but the rest of the wave will just go on as if there are no piers. If the wavelength is very short compared with the size of the piers, then again, there's going to be no diffraction. But if they're comparably sized, then that's classic diffraction, right? Some of the waves will reinforce each other if they're comparable to the size of the spacing between the piers. And then you're going to have diffracted waves going off at an angle. So, you've seen the diagrams in which basically after the waves move through, they go off in circles, reinforcing or not reinforcing each other.
mhm,
Now, we know in retrospect, well, that doesn't work because the interaction of the electron and the X-ray are the interaction of these two particles. So there are quantum effects that completely change those equations. He wasn't thinking about that. This is pre-quantum, and he's just saying, how do I put together the fact that I'm getting diffraction, but I'm getting too little total scattering compared with what I determined to be the size of the atoms. So basically, he's trying to say the electron is the size of the atom, but that didn't make any sense in terms of anything that would be relate to the electron's own self-energy. So the reason why he has the big ratio is that at the end of that paragraph, we have mc squared equals E squared over A. Well, again, that's a little hard to follow, but if you do an algebraic explanation, A is the radius. So A equals E squared over mc squared. That's called the classical radius of the electron, and it's quite small. It's 10 to the minus 13th centimeters. The radius of the atom is typically 10 to the minus 8th centimeters. So you have what should be a really tiny electron, but it acts as if this is optically as if it's this big thing.
mm,
So he took what we would call antenna theory and said, well, that can be if you have a ring, right? many of our antennas, in fact, are shaped as a ring. You have a very fine wire, but the antenna acts as if it's a solid object the size of the ring. And I won't go into the mathematics, but the way he calculated it got even worse because he ended up with the ratio as an exponent. So you got not only this big difference, which is a factor of 100,000, you got a much bigger difference, which was e to the 2,500. And of course, that's about 10 to the 1,000. So that's this astronomical number, beyond astronomical. So he was hypothesizing a very, very weird object. But of course, Einstein was hypothesizing something even weirder. So that's what he was trying to test. And obviously, he wasn't getting a big positive reaction. You saw what was Rutherford's reaction to this? Anybody?
At the end of that section, it says Rutherford brought him in to his class, and he said, I hope you'll listen to him attentively, but you don't have to believe him.
Right, and then
I will not have an electron as big as a balloon in my laboratory.
so he was reacting that this was pretty absurd. Our videos come out of LPPFusion's research in fusion energy, which will power a future with abundance for all, with a clean, sustainable economy and environment. Goods, housing, and infrastructure would be extremely affordable once fusion kicks in. Fusion energy is the key to an advanced future. Support fusion research. The link's in the description, and thanks. I'll just add a small note from much later in history. We'll get into this, but I was introduced to our device, the dense plasma focus, by a scientist by the name of Winston Bostick. And Winston Bostick, in addition to being a pioneer in fusion and plasma physics, he was fascinated with the idea of resolving what we're the question which we're seeing just emerge, which is wave-particle duality, and in particular, what is an electron? And there are many puzzles about what is an electron. But one of the most obvious ones is that if an electron is a truly elementary particle, which is the current hypothesis, it has no components, what's holding it together? An electron has negative charge. Negative charge repels negative charge. It should blow apart. So what he decided held it together was gravity. And there's a big problem with that hypothesis, which is obvious to him, is that the gravitational field at the classical radius of an electron is 10 to the 40th times weaker than the electric field. So the gravitational field attracting the parts of the electron to each other, absolutely insignificant compared with the repulsion. I don't know whether he's aware of Compton's work. I actually was not aware until I read this of the ring electron. But that's what he hypothesized. He hypothesized a ring electron in which its diameter, the diameter of the ring was the classical diameter of the electron. But the minor diameter, in other words, the diameter, let's say, of the wire that the ring is consisting of, was this exponentially small number designed so that the gravitational force was equal to the electric force. So the electric field would be spread out over the ring, but the gravitational force would be applied to the cross section of the ring. And if you made these ratios astronomically large, 10 to the 40th times, you could actually hold the electron together. So we'll get back to that in the future, but the ring electron sort of had an afterlife despite being destroyed by Rutherford. So what I find very interesting is, you know, Compton is basically trying one idea after another to try and reconcile these pieces of data, which is what wavelengths are diffracted by crystals and how much is the total scattering. So where does he take it from there? Where does this fluorescence come in?
I guess the fluorescence comes from the electron being excited and then dropping back and emitting a photon.
Right. So he's using this fluorescence to explain.
What he says is that as the electron falls from a higher orbit to a lower energy orbit, it emits the photon, and because it's moving at relativistic speeds towards the lower energy orbit, that will Doppler shift the photon it's emitting to a longer wavelength as it flies away from the atom,
Right.
from the electron.
So now this is not, strictly speaking, a classical approach, but it is something that doesn't require the photon as a quantum. So he's basically saying there's a strange type of fluorescence, not the same as the fluorescence that people had observed is always a delayed effect. So you put the energy in and gradually the atoms return to their base state. In the process, they emit the fluorescence, which is at a lower wavelength. So what was wrong with that?
No.
He didn't really find anything wrong with it, did he?
I didn't find anything in the text.
Right. Now, he was satisfied with that.
Mm-hmm.
Okay. So it was new experiments that caused him to rethink what he was doing. Annette, did you do this reading?
I didn't. I'm sorry to say. I will.
All right. So that explains why you're so quiet. I think it's pretty easy to follow, so I think you should do it. I think you'll find it interesting.
The X-rays experiments.
Right. So this is what gets into the funny thing, is that he starts doing his own experiments in terms of recording the primary X-rays and then the secondary X-rays from Pyrex and graphite scatterers. So what does he find?
The wavelength of the secondary X-rays is larger, greater than the one of the primary.
Right. Now, what's happening here is by 23, Einstein's theory of special relativity is completely well accepted. So people know that there are relativistic effects. He's trying to integrate those relativistic effects because these are high energy X-rays producing electrons, and he's trying to understand how relativistic effects could affect the wavelength of light produced. And if you look at figure 3, people all have a copy of this, either paper or on their screens.
Yeah, just let me get to the figure.
Yeah. I don't know whether I can share the screen. So.
3, yeah. Page 983.
Page 983, figure 3.
Yeah. Yeah.
So basically, this is the original figure. And he thinks that the secondary peaks are those little peaks at 10 degrees angle.
Yeah.
And what the present author, the historian, is saying, he was ignoring at this point that that big peak had moved.
The huge one at 6 or 7
Right,
degrees.
right. So this is what he calls the author, the historian's plot of Compton's data. Obviously, if Compton had plotted the data like this, he probably would have noticed it immediately. But instead, he's saying it's the secondary peaks. So that's what his conclusion is in December of 1921. But he's a better experimenter than being satisfied with this. So I'll just read this. By October 1922, so this is 10 months later, when he published a National Research Council report, Compton realized he had misread his experimental data. That is, he realized the shift in wavelength between the secondary and primary was not 35%, which he couldn't explain by relativity or anything else. But he tried to by the fluorescent theory. He now stated the ratio was 0.969. So instead of 35%, it's approximately 3%.
Mm-hmm.
But he stuck with the theory. So this is a big change. Your experimental data is telling you something 10 times off, but it's a natural human phenomena. You're fond of your own theory. So he says this can be explained by conservation of momentum. But this time he's doing the math wrong. It's actually a subtle difference in the equation, so it's understandable, but it's a big difference in the hypothesis. So finally, a month later, he decides to use the quantum hypothesis. And he says, okay, if we have two particles interacting, then he does a correct analysis within relativity of what the result of the two particles interacting. So what's really happening, and now after years of experimentation, he realizes, is you have what can be understood as a simple particle-particle interaction in which the high energy photon comes in with energy, with momentum, and hits the electron. The electron absorbs energy from the photon, and the photon moves on with less energy and therefore a slightly lower frequency. So now when he does the relativistic interaction correctly, he arrives at a number that exactly corresponds to experiment. So he publishes the same data with the slightly changed equation, but it's an equation derived by a completely changed hypothesis. This is no longer fluorescence of a wave being absorbed by the atom emitting another wave. It's a photon interacting with an electron that was bound to the atom, and the photon moving on with less energy. So as the this is submitted in December of 22 and published in May of 23. So it only takes him a couple of months once he realizes his mistake in what is the secondary peak to arrive at the correct theoretical prediction. Now, this author is unsure of exactly how much he was even at the end relating to Einstein's work, but obviously he knew of the hypothesis. Peter.
I was just going to ask you, because his penultimate theory, it says here, Compton assumed that the velocity v of the electron oscillators in this revised fluorescence, relativistic Doppler-shifted fluorescence, was determined by conservation of momentum. But I thought at that point, the idea of electromagnetic waves having momentum wasn't understood. So I'm not quite sure how that can be right.
No, it was understood. In other words, in the development of Maxwell's theory during the late 19th century, where it was applied to the very rapid development of electric technology, and especially to the question of how telegraphy was to be transmitted over very long distances. It became realized that, and I don't know who realized it, whether it was Maxwell or Heaviside, that you could derive from the electromagnetic
equations, yeah,
transfer of energy, and at a much lower level, the transfer of momentum.
Right.
What we call light pressure.
Okay.
So that was something that was compatible with wave theory. And again, was very different from the question of the photon, because the question of the photon is you immediately got into the question that Einstein himself did not address in 05, which is how can it be that light both acts as a wave and as a particle? Because once it was accepted, and Compton results in 23 made it widely accepted that there was this particle nature that Einstein had proposed much earlier, 18 years earlier.
Right. Okay.
You had an enormous technology based on the wave nature of electromagnetic phenomena, electromagnetic waves. So that immediately posed this paradox, which, this is almost exactly a century ago. We're talking in 2025 about work done in 1923. And in the succeeding century, this has remained a very lively topic of discussion among physicists, to say the least, which is this wave-particle duality. Is this all clear? Sam?
It does seem amazing, doesn't it, that if they had, for the 20 years earlier, had identified that light or photons had momentum, that it took so long to get to this hypothesis. But I guess, yeah.
Right.
Yeah, I was kind of thinking about. I'm like curious what Einstein was doing the whole time. Like, did he
Well,
just switch over to relativity?
No, he didn't. Some of this we have to get into in the next session, where we're discussing the Bohr atom. No, Einstein was very active in the discussions about quantum theory from the start through to the end. I mean, the short answer is I don't know, and I think that's interesting. If anyone wants to research this, I'm sure his biographies or something on the web will come up to the answer.
I mean, he must have been reading successive theories of what was going on from
right. The
quantum,
question is, how did he react? I mean, it's two questions, which I think we should go into in the next session, even though the main focus is going to be the Bohr atom. Was it true? I mean, we're talking about the difference between the linear myth and the messy reality. So was it even true that what Stoyer says, or is he really pushing the wand too far in the other direction? Was it really true that by 23, almost nobody still accepted that photons existed? I don't know. What, was there, you would more or less think that in such a long period, I mean, this was a period of revolutionary change in physics, that Einstein's view must have been attracting some adherents in that long period. So I think that would be interesting to look at, and how.
Yeah, especially.
What?
Oh, go. No, you can go.
Go ahead. What?
I was going to say, especially if relativity was so accepted by then already, you think people would be like, maybe this guy's onto something.
Well, yeah, there wasn't so much of that. There wasn't so much of, no, I don't think, I mean, historically, we know that one thing that happened was the development of special relativity during World War I, and then immediately after World War I in 1919, the first confirmation of special relativity with the observation of the bending of starlight during the 1919 solar eclipse, and Einstein becoming a prominent public figure, not only a prominent scientist. And of course, the Nobel Prize comes in there somewhere. I don't know what year he was awarded the Nobel Prize. So obviously, there's an evolution that is worth thinking of, because we've jumped forward. Well, remind me, what was our last class was?
Our last class was
Rutherford?
alpha and beta scattering by matter.
Yeah, so
and
Rutherford is back
structure,
in.
and Rutherford's never done the alpha particle experiment, scattering experiment.
Right. So Rutherford, we were talking about 1911, right?
Yeah, 1911, yeah.
So obviously, historically, we've skipped over a rather important period, which is the period of the First World War. and, you know, landed essentially 12 years later. So yeah, I will see whether I can come up with some. I mean, my time is very short, but I'll see whether I can come up with some other references.
Well,
But I
maybe,
invite you to, I mean,
you know, during the First World War, scientists, I mean, the number of conferences and people moving around in Europe for scientific conferences was reduced somewhat due to the
it was
war.
eliminated. I mean,
Yeah.
yes, the World War completely disrupted.
Exactly. So there was not that much in exchange, and maybe that reduced, slowed down
Yeah.
the
No, there was
velocity
no
of.
doubt that it was very disruptive. I mean, it was difficult to even communicate
Yeah.
by writing across the front
So
line, as you can
that
imagine.
might be at one of the causes of how long it took for people to
Right.
admit the fusion of photons. Yeah.
Right.
Was there also maybe an element of like we already had working technology based on the wave theory, so maybe there was like less incentive to look deeper into what was
Yeah.
going
I
on?
think the biggest problem is
That's true.
paradox. In other words, you know, until the development of the completion of the development of quantum theory in the late 20s, going on to the early 30s, there was an obvious reluctance to consider something as bizarre as wave-particle duality. I mean, dualities were basically things that were off in philosophy, you know, mind-body duality. You know,
It has to be one thing or the other. It can't
yeah,
be
I
both.
mean, certainly in science, that was the case. So and you know, I don't see that in any way Einstein addressed it, at least in the initial paper. Again, it'll be interesting to see. He was very big on logical consistency, so I'm sure he thought about this. It's certainly true that during the war years, there's no doubt that his focus shifted to general relativity. That's what he was working on. He wasn't working on quantum problems during the war years. But again, the war years are a relatively short period out of this 18-year gap. So I do think it's useful, and I encourage people. A lot of this information is, you know, just searchable online. But I will also do it. I have, you know, a few steps away, a couple of really good biographies of Einstein. So I think that that'll probably be the shortest route to get the information on what's happening during this period. But yeah, part of the answer was he was certainly concentrating on general relativity. He got, you know, here this was something that was recognized as revolutionary, not only by his colleagues, but very rapidly by the mass media. So I'm sure it took up a lot of his time.
And then in kind of a roundabout way, it led to Compton's experimental validation of his
right, but the question
photon theory.
is, you know, after the World War, there's no doubt that everybody went back to thinking about these problems that eventually led fairly quickly in the course of the decade following the end of the World War to quantum theory. So there is a part of the story that we're skipping over. So definitely I'll try and find some readings that can fill in that gap. Let me ask everybody, we have to wind up at, it's 4 o'clock. I was thinking, we've been continuing with the same group. People who are not part of this group have been asking me about the series and wanting to join it. I don't want to get to a large group, but without spoiling the discussion, do you think that we could have like 20 people, or would that be too big? What would, let me put it positively, what would be people's ideas for the maximum size that this group should be? Anybody?
I think it'll be naturally self-limiting, so I wouldn't worry about it too much.
Yeah, I would. It's the same feeling. I have the same
All right.
feeling.
You think that people won't stick with it? All right. Well, then I will advertise the next one so that we get fresh blood.
I think you could have,
Is
I
it
think you could have 100 people
appropriate to your background, Peter?
who don't understand.
Blood red background. So yeah, we will be advertising it. Any ending comments?
I think you could have 1,000 people who didn't understand anything you were speaking of, and it would be a manageable size.
Eric, I just want, I'm just really struck at the very closing paragraphs, to bring this all together, where the author says he's established a reality of light quanta on the same ontological level as electromagnetic waves, radiation embodied a profound, this is the take home, radiation embodied a profound wave particle dualism. So you kind of come full circle from several angles to the paradox
The final paragraph of Stewart?
of the Annal of Physics. Is that Stewart? The one we've been looking at. Stewart.
So he says,
this is on page 988.
right, this is the historian recognizing
Right.
this duality, right? But the question is during this period of 05 to 23, what did the physicists themselves think? Because the question of the duality was really raised in 05, as soon as Einstein said, there are, the evidence is there are photons. Because as soon as you say there are photons, then you immediately have this duality. So the question is, what in the period 05 through 23, what were people thinking about this? Or were they just,
Well, it looks like
I want to think about that.
narration, they were in one camp or the other. So they were trying to get classical solutions. And then they were, fishing around with Doppler effects and everything else to kind of.
Well, that's certainly what Compton was doing.
But wasn't everyone else more or less doing the same thing?
Well, the question is, as I say, I can resolve it pretty quickly. What was Einstein doing about this duality? Because, as I say, he was big on logical consistency.
After it's only 18 years, I mean, in the future, they'll look back on us and say, why did it take 70 years from the discovery of the dense plasma focus to actually do anything with it?
That's right. Well, that I pretty much know the story.
The expert witness.
Yes, as a witness to most of those years, not the earliest part. I was in school, but yeah, well, it's sort of a different question. But anyway, I'm not saying that the answer is mysterious. It's just that we don't know it, so we should try and find it before the next class. I got to sign off, guys. So
Thank you, Eric.
Thanks a lot.
Thank you, Eric.
Eric.
Thank you very much.
Thank you.
Thanks very
Bye,
much.
everyone.
Cheers.
Bye, everyone.
Our videos come out of LPPFusion's research in fusion energy, the energy which will power a future of abundance for all, with a sustainable economy in a clean environment. Goods, housing, and transportation will be affordable to all once fusion kicks in. Fusion energy is the key to building a better world now. Support fusion research, $10 a month at lppfusion.com/support. The link is in the description. Thanks.